Hello. Today we're going to talk about Topic 4, Section 5, Probability and Expected Outcomes. All right, so this starts our probability section. It's one of the hardest sections in statistics and in math. Probability is just something that people miss a lot. Okay, so make sure you're taking good notes. So there's two different types of probability, experimental and theoretical. Experimental is based on past events. Okay, so seeing what's happened in the past, testing a new drug treatment on patients. You're seeing what are the odds of that drug helping the next person based on whether or not it helped people in the past. Theoretical probability is determining logic using a more deductive method. So theoretical would be like rolling a dice. Or rolling a die. You know that the odds of rolling a 1 is a 1 in 6 chance. Okay, so actually having rules and standards. Okay, so regardless of how you calculate it, it's still how likely something is. You have to remember that just because the probability is low doesn't mean that it can't ever happen. Okay, a woman could have triplets in her first 4 pregnancies in a row. I mean, gosh, that would be really hard, but it's very unlikely. But it still could happen. Okay, that's what you need to know about probability. Now, for the vocab. All right, so let's knock it all out. So, random experiments are those where we don't know the exact result in advance. All right, but we know all the set of possible results. Okay, so random experiment would be like rolling a die. Okay, we know that all the outcomes are 1, 2, 3, 4, 5, 6. Okay, so the number of outcomes we denote this way is just 6. Now, any subset of a sample space is called an event. Okay, so rolling a die, a subset of 2 would be described as, rolling a dice with the number 2 on it. Okay, the subset 1, 3, 5 is an event that's described as the face is odd, rolling a number that's odd. Okay, an event can consist of 1 or more outcomes, so it can either be 2 or it can be 1, 3, 5. Okay, and each time an experiment is repeated, it is considered a trial. So this was the first trial, and then this was the second trial of rolling. Oh, I'm sorry. These aren't trials. Actually, rolling your dice is considered a trial. Okay? So rolling a dice and getting a 5 is a trial. Rolling a dice and getting a 3 is a trial. Okay? Okay. I really need to stop saying okay. I know I say that a lot. It's because I paused the video and it's my filler word. Sorry. All right. Put another filler word in there. A coin is flipped 4 times. So what is all the possible outcomes? Well, you could get 0 heads, 1 head, 2 heads, 3 heads, or 4 heads. And then you could literally list all the possible ways you could. That's time consuming, all right? But not so bad for this occasion, but some outcomes take a long time to calculate. Okay? So these are all your different options. Okay? Now, what if I wanted to flip the coin 4 times, but this time I only recorded the number of heads? What's my sample space now? Is this the same sample space? No, because I don't care if I got a head, last, or if I got a head first. Okay, so this would just be a sample space of either getting 4 heads, 3 heads, 2, 1, or none. Now, probability is always a fraction or decimal between 0 and 1. Okay, these are your formulas on how to get it. Okay, if it's a 0 probability, that means it's never going to happen. Never going to happen. Okay, if it's a 1, it's always going to happen. Okay, it's a 100% chance of happening. Okay, 0.5 is the equivalent of 50%. So 50-50 chance of it happening. Okay. You need to know what kind of value, all right, what gives you what kind of chance. And again, just like with correlation, this is subjective. So it depends on what you're looking for. In the IB exam, it will be very clear cut. Okay. So they're not going to give you something and ask you, is there a good probability of this happening? And then it be 0.5. It's either going to be 0.9 or 0.1. Like it's going to be extreme. Like it's going to be, I was told it was going to be very obvious. All right. Okay, so let's do some examples. So 4 boys and 6 girls are waiting to see the doctor. Didn't remember who arrived first, so just chooses them at random. What's the probability that a boy is chosen to see the doctor next? Well, think about what you have. There could be, you only want one boy. So this is what I get a lot of. I get a lot of times kids are like, oh, well, we want one boy and there are 10 kids to choose from. Okay, do not do this. This is wrong. Do not do this. Okay, because there are 4 boys. Do I care which boy it was? No. So that's going to be 4 out of 10 or 0.4%. Or I'm sorry, 0.4 probability. Sorry, it'd be 40%, but 0.4 probability. They wanted the probability, so they wanted it as a decimal. Okay, so for a normal 365-day year, find the theoretical probability that a person has a birthday in August, assuming that a person is equally likely to be born on any day of the year. Well, how many days are in August? 31. So I want 31 out of 365 days. That's the chances, or the probability of being born in August, 0.08. So usually when we describe the probability of an event A happening, you usually write it where as a box represents the outcome of everything. Okay, so 100% of every single outcome. That's your set of every outcome. The probability of A is this circle, and the complement of A is not A. Really, that's what it is. It looks like an apostrophe. I mean, well, it is an apostrophe up there, but that's spoken as not A. So what is the probability of A happening? What is the probability of not A happening? Okay, so together, A and not A should make up 1. Okay, so find the probability that a person does not have their birthday in August. Well, I could count every other day, right? That's not in August, okay? Or I could just do 1 minus the probability of August. So 1 minus our previous probability, and I get 0.91. So much more likely that it won't be born in August, right? Anyway, that's how you do complements. So expected outcomes. It's much easier to describe it with an example. So you're drawing a card from a deck of 52 cards. Okay, so imagine that this isn't a standard deck. You've got 4 colors: red, blue, green, black. Okay, instead of your spades, aces, spades, clubs, diamonds, hearts. Okay, so you've got these 4 colors. You choose a card at random, note the color, and then put it back. You repeat that until you record 24 cards. Okay, so you write down 24 colors. How many would you expect to be green? Well, in a perfect world, my recording has to match my deck. It should be the same thing as, it's like pulling the 24 cards is like pulling a sample of my deck. So I would hope that my sample would match my deck perfectly. So in my deck, there are 13 green cards. So that is 13 out of 52, or 1/4 of the deck. So we do n times the probability of getting x. Why did I write college degree? Oh, that must be from the old one. Okay, so the probability of x. So the expected outcome of x is the number. So there's 24 cards times the probability of getting a green card. So that would be 1/4. So we should expect 6 cards to be green. We expect 6 cards to be green. Okay? Just making sure that doesn't look like a B, because it kind of did. Let's do some more examples. All right, so we're going to play a game, and we're going to roll 2 dice and add the numbers, and then let's see, if each player rolls the dice 12 times, how many times you would expect the dice to add up to 5. So we just record the sum of the dice 12 times. Well, let's see. I know that there are 6 numbers on the first dice and 6 numbers on the second dice. So there are 36 total outcomes. And if I want the sum to be 5, well then it can either be, I can either roll a 1 and a 4, a 2 and a 3, okay? But I can also roll a 4 and a 1 and a 3 and a 2, okay? So there are 4 options that I'm looking for. Okay, or that I want to happen. So, how many times would I expect the dice to roll up to 5? Well, what's the probability of rolling a sum of 5? That would be 4 out of 36, or 1/6. So, our expectation of getting a sum of 5, we have 12 times we're rolling the dice, and 1/6 of them should be a sum of 5. So we expect to roll the dice twice. Okay. Wait, hold on. How many times you would expect the dice? Okay, so I just messed this up like completely because I'm a goofball. And 4 out of 36 is not 1/6, it's definitely 1/9. Yeah, I don't know what I'm thinking. I'm like wondering why I'm not getting the right answer. Because I divided by 6 apparently. Silly me. So we have, also, we want to determine how many times you would expect the dice in this game. So each turn, all right, each player rolls. Okay, so that means we're going to roll 12 times per 3 people. So there are 36 rolls, and 1/9 of them should add to a sum of 5. So that's why our answer is 4 rolls. That's what we expect to happen. All right, so then let's see, example 3. In the game described in example 2, someone rolls a 2, 3, 11, or 12. They automatically lose all their points. Ooh, how many times can you expect the players to lose without losing all their points? So let's find the probability that you're losing your points. Okay, so I could roll a 2, so that's rolling a 1 and a 1. I could roll a 3, so that's a 2, 1, or 1, 2. 11, so that's a 5 or 6, or 6 or 5. And then a 12, this is just 6 and 6. So there are 1, 2, 3, 4, 5, 6. 6 out of 36 total ways. So 1/6 chance of losing your points. Okay, so we want to lose the probability of not losing. So probability of not losing is 1 minus 1/6. So that's just 5 out of 6. That's a rough looking 6. Okay. And then we want to see what all the players expect. So the not probability, the expectation of not losing. Well, we're going to roll 36 times, 12 times for each person. And 5/6 of that is 30 times. So we're expecting to not lose your points 30 times out of the game. Okay, but we know how games work, right? Sometimes you just feel unlucky and you lose your points every single time, okay? Even though the probability says otherwise. All right, so this is everything you should know in this section. But one thing we didn't really cover in the section, which I'm really surprised at, is we didn't really cover the tables. So I thought we would just do an example. Okay, so let's see. A political strategist surveyed 100 people asking their opinion about a new proposal. The results are summarized in the contingency table. Most of you have seen this before. All right, so just to kind of recap what it is, we know that there are men and women that were surveyed, and then they were recorded whether they approved, disapproved, or neutral. There was 100 total responses. So of the men, there were 46 total men, which means there has to be 54 women for a total of 100. Okay? And if there are 46 men, and we know 3 are neutral and 19 disapprove, well, 19 plus 3 is 22. 46 minus 22 is 24. Okay, when we add these up, okay, it should be the total men. Same goes for the women. 33 plus what plus 9 is going to give you 54. Well, 33 plus 9 is, what is that, 42. So 54 minus 42 is 12. We can also look this way. 57 people approved, well, 24 men, 33 women, that is 57. Disapprove. 19 men, 12 women, that's a total of 31 who disapprove. 3 neutral men, 9 neutral women make for 12 neutral people. Okay, so here's our contingency table. We want to find the probability that a person chosen at random is a woman who disapproves the proposal. So women who disapprove would be right here. So that's 12 people that I'm looking for out of a total of 100. Okay, so 12 out of 100 is just 0.12. Okay? All right, if you have any questions about contingency tables or any of this probability, please ask me in class. Probability gets hard. I promise you are not the only one with these questions. You do not sound dumb if you ask me these questions. Stat is very weird and you have to get the wording right. So I have to, you'll even hear me when I answer your questions. I will pause and take a minute and think about what I have to say before I answer your questions. Okay, because again, probability is easy to mess up if you can't get your words right. Okay, all right, I'll see you in class.